Hi there, I'm Samantha Snabbs, and I'm here today from our Austin factory in our operations building. So honored to connect with the FGF User Group. I know we all have a lot to learn and share from each other. It's nice to see some familiar faces. Just for context, this is being recorded, and we'll have an opportunity to hear from our speaker and then have recorded Q&A. We'll go ahead and turn it off for offline Q&A. If at any point you have a suggestion on someone else that can present or a different way we can structure this, please share it with us. We hope this is a resource for you. But today we have a treat because we have Daniel Fernback with us, who's from JuggerBot 3D. They've been slugging it out as long as we have, and even longer in the FGF vertical in Youngstown, Ohio. And we're so honored to be peers in America Makes with them in that community. And so it's going to be really cool to hear what Dan has to share about their adventures printing with pellets. Dan is a Youngstown native almost, right? Because you've been there a pretty long time.
Yeah, born right outside of it. Born and
Yeah.
raised.
If anyone hasn't been to Youngstown, please check it out. And the America Makes community, what they're doing there is just phenomenal and is an accelerator for the U.S. But Dan's had a long tenure with 3D printing and being passionate about it. He was actually the student ambassador to additive manufacturing at Youngstown State University, where he graduated with a bachelor's degree in industrial and systems engineering, and then has gone on to have other ventures to include being the co-founder of JuggerBot, which you're going to hear more about. They're now, looks like almost 12 years old, according to y'all's LinkedIn. Is that right?
Mm-hmm. Yep, goes quick.
So true pioneers in the community, and we have so much to learn for them. So I'll go ahead and turn it over to Dan to share more, and yeah, look forward to the follow-up conversation.
Thank you, Samantha. I'm going to go ahead and share my screen just so the presentation gets pulled up. Can you guys, somebody let me know when you can see this, please?
Oh, I can see it on my end.
Fantastic. Thank you. So again, I'm happy to be here. As Samantha mentioned, my name is Dan Fernback. I am one of the co-founders and vice president here at JuggerBot 3D. We've been in business since 2014, and we are located in Youngstown, Ohio. Our specialty is really in large format 3D printing. But we started in 2014, coming right out of Youngstown State University. Me and my fellow co-founders, we were all engineering students. Just as a kind of a quick aside, the way that we got into this space was always having a love for making things. It was always very interesting to us. And as serendipitous as it would be, in the 2012 timeframe, we had a manufacturing processes course with a professor named Daryl Wallace, who was at that point in time very involved in writing the proposals or helping in the proposals that brought America Makes to Youngstown, Ohio. So we were fortunate to learn about 3D printing for the first time, really for the first time, in the light of true manufacturing environments. Right. So in the 2012 timeframe, I think a lot of the hype around 3D printing was just starting to build. It was still predominantly being used as a prototyping tool, which is great. And obviously that's still a really strong area of use for 3D printing. But he had introduced it to us right alongside machining and injection molding and casting as something that could make a big difference for manufacturing and have a big impact on not just how we make things, but really how globally the world is interfacing with digital manufacturing. So we built on that upon graduation, or rather before graduation. We were interested in how we could, what kind of manufacturing business essentially we could build that was centered around 3D printing. And we quickly came across a lot of the challenges that you guys have probably heard about from time to time over the past decade and a half, where the limitations were. And a lot of that's still, a lot of those have been addressed, but there's still opportunity and room for improvement, ranging from material compatibility to reliability and scalability. And that's where we really placed our hats. So we started off making filament-based printers, smaller format, but always focused on engineering and high performance grade materials and having an open source material architecture. And then in the 2018 timeframe is really when we officially got into large format, quote unquote, large format 3D printing. It was about that time that we got into pellet fed 3D printing as well, or fused granulate fabrication. And in 2020, March of 2020, we officially launched our Tradesman series, which is still a product or a product line that we offer today. And I'll talk a little bit more about as we work through the presentation here. So I've got a quick case study I want to share with the group today. We get a lot of questions from folks who are using filament printers and have experience with that. And one of the tough things is that there's a lot of reason to be interested in pellet 3D printing, whether that be from a material cost standpoint or material availability standpoint. And one of the challenges is helping those folks understand how it directly compares against, from an FGF standpoint versus an FDM or FFF standpoint. And seldom do we have a very crystal clear upfront initially way of being able to show them what they can and cannot do with FGF in a way that they might be able to do today with FDM or FFF, because we know there is a distinction between applications and when and how you use each technology, and then how that really transfers over or results in benefits for them directly. So this is a case where we have benchmarked information against large format FDM printers, which was nice. And it's a real case study that I've actually talked about a couple of times over the past couple of years. But again, it's I think a great demonstration of how FGF 3D printing can help, quite frankly, from a prototyping standpoint and from a production standpoint, and really helps transform how engineering teams can bring products to market. So we offer at JuggerBot 3D a growing variety of large format printers. Everything we do right now is gantry based. We have heated chambers and closed chambers across the board. And people typically come to us because they're trying to utilize the technology for higher performing types of materials. And that could be, again, polycarbonates and nylons. It could be reinforced composites. We have a number of users who are printing with PEI on our systems, especially for some tooling applications. And where those, where that kind of system architecture is really important. It's while I have up a brief overview for our products and service offerings, the machine that I want to just tie into on this discussion is our Tradesman Series P344. Which again, this is the machine that we launched in March of 2020. So it's been available for almost 6 years now. And so back in, I think this was 2023, we had done a project with this system that really made good use of, again, the architecture and some of the, let's say, additional aspects of the additive manufacturing system, the P344, that doesn't always get talked about, because if you're not using FGF printers, like hopefully most of the folks that are watching this are considering, they don't realize what kind of challenges or differences and nuances there are in operating a system like this versus a more conventional 3D printer. So our Tradesman Series P344, we'd actually consider a medium format FGF system. Most of the folks probably know that are watching this, FGF 3D printing was really first commercialized in like the 2014, 2015 timeframe. And there are systems that have travel distances of 10 to 20 feet by 5 to 10 feet by 5 or 6 feet high. So the Tradesman Series P344 having a build volume of 3 feet front to back, 4 feet left to right, and 4 feet from bottom to top, we consider a medium format system. But it is definitely on the larger side when you look at the 3D printing market holistically. And we'd like to say that it is self-contained and standalone. And so just kind of the call outs here, we'll walk you through some of those. All of our systems come equipped with and integrated with mobile drying units, because obviously it's very important to control the moisture within the materials to make sure you have repeatable and reliable results. Again, all of our systems are enclosed, insulated, and heated. And then we have integrated workstations with all of our systems, which includes all the controls and all the software that you need to really be effective with a system like this on a machine, in a machine shop, on a production floor, or out in the field. So one of the things that we don't get to talk about that much that's relevant to this case study is addressing some of the challenges that are, again, unique to pellet 3D printing. So a lot of times we see folks who kind of like transfer over from the FDM or FFF world, where they get hung up on developing process parameters, which is understandable. We see the operation of machines like this as a skilled trade. And so without getting too deep into the weeds, a lot of the challenges really are derived from two primary pain points. The first is that there's a lot of variables, a lot of additional variables that the operators need to take into consideration, or process engineers, who's ever developing the parameters for a specific material machine configuration combo. Lots of variables that you have to take into consideration and understand how changing those variables impacts printing outcomes. And then specifically for direct pellet extrusion, it's dynamic by nature. So the way that the process scales with different shapes and sizes, especially size parts that have maybe like a very wide base and then it kind of comes to a head like a pyramid. To develop a more complete set of parameters for a build like that can be very, very labor intensive, and it could require a lot of guess and check if you don't have the right tools or experience in place to do that. So seeing that being, understanding that skills gap is a barrier for folks to take this technology and leverage it to their own benefit. We have worked, as some others have as well, to develop tools that can make it easier and streamline production. So the way that works for us is largely through what I call our software stack. And it's really rooted in automated calibration for the normal things, right? Bed leveling, bed mapping, nozzle height adjustment, but also our bead characterization system. And essentially that you could think of that like a fourth sophisticated calibration program for melt flow, right? So it's actually taking real data off of a printed part specimen, and this can all be done in about 30 minutes, and then using values off of that printed part to create a material model, which will then provide the machine with the insights it needs to effectively set the RPMs of the motor based off of the acceleration of the gantry system to maintain a specific bead height and layer in bead width, right? The bead geometry for a specific part. So without getting into the rest of the details on this page, that's important because this project I'm going to talk about was the first time that we really put the BCS to the test internally. And it made a big difference for us, which I'll tie into in a couple of slides. So, again, it's not hard to, I think, provide the value proposition, at least at a fundamental, kind of from like a ground level for pellet fed 3D printing. For those who are using filament 3D printing, typically comes down from material, right? And so in this case, our customer was working with a 3D printing service bureau that had a farm of Fortis 900s. And Fortis 900s are great. There's, they're in my opinion, kind of the premier large format filament based system out there. They've been around for a long time. It's a machine that does a lot of good work. But we always hear from folks that it's really expensive to use their materials. So we can put a chart like this in front of them, and anybody can do this. You can do your own independent research and say, well, what are my material savings if I go from running parts on my Fortis machine to a pellet fed system like the Trason Series P344? And these are obviously very significant types of savings. But there's way more to the story. This was important because of how it transferred over to the economics of both the prototyping and production for the case that I'm going to talk about. But I just want to capture it here real quick as a lead into the case study itself. Okay, so again, 2023, we were approached by a company that's in mobility and entertainment systems. Their parent companies in oil and gas, but these are folks who would make mobile solutions for Disney World and Universal Studios, and they also had a line of mobility solutions, or still have, I should say, a line of mobility solutions that also branched out to municipalities and resorts, and in this case, airports. So what you're seeing here is a people mover. So this is an autonomous or semi-autonomous electric vehicle that will just transport folks to and from their gate at an international airport. And when they were coming, traditionally this would be made, the cabin itself would be a fiber reinforced molded piece, so an FRP molded piece, in which case, they need to prototype the actual cabin, and then they need to move into production, which is going to require additional engineering time, additional cost, additional lead time to create the tools that are going to be used to mold the parts, in which case then those molded parts would be, after they're molded, they would be bonded together, fabricated, post-processed to get to that final look that everybody's looking for. So when they came to us, that the customer was in a bit of between a rock and a hard place. They had SOP dates from their customer that were coming up very quickly. They had budgetary restraints in terms of how much they could apply to prototyping and tooling. And after working with their traditional vendor, with the Pharma 4-900s, they were kind of meeting a dead end in terms of what they could do to just get prototypes made before they invested the money and time into tooling. So they had never used FGF printing before. They were just asking us if we could basically meet their budget and lead time for prototypes initially. And after reviewing their parts, the material that we essentially told them they should be using was just a carbon fiber reinforced ABS, which is a great material. We consider it more of like a lower level, not a commodity material, but a more lower level engineering grade material. Very good with durability, prints really well, cost effective, and was comparable to what they were asking for off of the FDM systems. We essentially worked with their engineers to be able to section and segment the design so that it could be printed in as little days as possible. What we were up against was what we were seeing from the Fortis users was that to make this cabin was going to be about 6 weeks of printing and $60,000 for our customer, which again was not what they had in their budget and didn't align with their customer timing. So after going through this process, I have another slide to kind of walk through how we segmented and how it was printed. We were able to print a cabin in 8 days. So it was 8 straight days of printing. And we were able to do that in 42 sections for about 20% of the cost compared to what they were getting from the Fortis users. That's largely stemming from the material cost savings that we were able to capture for them, as well as the heavily reduced amount of machine time because of how big these parts were. So each cabin is about 42 sections. We did have a couple filament parts in there as well, based off of how we segmented the parts and how the tolerance stacked up. We did use some filament printed parts as well, but there's only 2 or 3 on there total. And in total, the weight of the cabin is actually north of 400 pounds. I think it was between 400 and 450, so it's called like 410 pounds total, which for us I think was only working at like a 8 pound per hour throughput. So that is obviously a significant savings, really helped them out for their prototype. Now, when we sent their first prototype to them, they did some internal testing on those parts and derived themselves that the printed cabins would be plenty sufficient for actual use, right? So now they went from, hey, we were able to make up our cost and timing that we didn't have to prototype. Now we can actually skip tooling altogether, and we can adopt a more agile production method here that typically only gets, it's kind of like a luxury of software engineers, right? We can put a product out there. If we have to make changes, we can make them without any significant penalty to cost or time. We can tailor the cabin for different vehicles or different customers. We can customize things as we need to based off of the capabilities of FGF printing. So moving out of that, we essentially went from just being their source for a prototype to their source for a run of, initially it was 6 cabins themselves. In which case, again, this next slide kind of shows you the process we walked through. We had used heavily, with support of our bead characterization system, we were able to effectively batch the printed parts together with high confidence that based off the layer time for this specific material and the nozzle size we were using, we could optimize the number of parts that were being printed at any point in time. And that's what really helped us get down to that 8 days per cabin. And it's also beneficial because, as you can see from these pictures here, there's a lot of material that's being laid down. These were still fairly long prints. I want to say that the average number of hours we were printing per day, each of those 8 days, was somewhere around 12 hours. So if something goes wrong at hour 6 or God forbid hour 10, there's a lot of, not just wasted time, but a lot of wasted material in a program that didn't afford any kind of loss. So the BCS system was really helpful in being able to give us the confidence and execute in this kind of manner. After the parts were printed, my title slide has a picture, but we did the bonding internally. We had a fixture plate to make sure that the builds were going, that they were consistent. We just used an off-the-shelf structural epoxy and butt joints. We didn't do anything too fancy for the joining itself. Once they were assembled here in Youngstown, they were sent down to a body shop, the same body shop that would actually be finishing the FRP molded cabins down in Florida, in which case they added a filler, they sanded it down, primed it, and then they, in the top right picture, you can see they painted it with a textured paint so that these running right now, the cabins that are still in use, you wouldn't know that they're 3D printed unless you were listening to this discussion. This is essentially like a monocoque chassis. So they did, after it left the body shop, it went to our customer's production site, in which case it was put on the electric chassis. They added lights, they put interiors into it, and there are about a half a dozen of these that are in operation today. Yeah, so again, just a fun example of how FGF printing can be used both to support prototyping and production, and it is a good example to give kind of a more apples-to-apples comparison from how FGF compares with large format FDM or FFF in the right applications. So again, short and sweet today, but wanted to share that fun one with you guys. We are more than happy to help support both the growth of this user group and anybody who's interested in getting into FGF. My contact information is displayed here, and I thank you guys for your time.
Thanks, Dan. That was super interesting. I'm going to read this question. Oh, it looks like David's still on, so I'll let him share his question in person.
Yeah, I'm still here. I have a visitor who's going to be coming in any minute. Just a heads up. I did have a question or two on the application. Do you have a sweet spot in terms of your road height and like the layer height and road width in the different parts that you made?
Yeah, so in this case, our P344, the standard nozzle sizes are 2 millimeters, 4 millimeters, and 6 millimeters. And we've done some work with some smaller nozzles too, but really the way the extruders are built and what they're tuned for is to operate within those nozzle sizes. I'm pretty sure in this case we are using a 6 millimeter nozzle. And so our rule of thumb as a starting point is always for the bead width to be 150% of the nozzle diameter. So at a 6 millimeter bead, we're looking at about a 9 millimeter bead width, and that we use a 4-to-1 ratio as a starting point for the layer height. So in this case, it'd be like 2.25 millimeters.
Yeah. Okay, that makes sense. Yeah, I am surprised that you're that thin, but it does make sense in terms of cooling and everything.
Yeah. And in this case, I think those are all all the wall thickness is 2 passes of the extruder, so it'd be about 18 millimeters, like 3/4 of an inch.
Yeah, come on in. Yeah.
Thick. So
all right. Hey, I do need to run my visitors here, so thank you very much for the presentation. Really enjoyed it, and look forward to meeting you in real life. All right, I'll see you.
Thanks. And then he'd also had a question. Did you use similar print settings for the 42 sections? He says, I'll check out the YouTube afterwards.
It was the exact, yeah, so yes, the short answer is yes. We used the same parameters across all 42 sections with the exception of the parts that were made from filament. We have some filament printers in house that we made. The lenses, I should say the enclosures for the headlights, those were printed on a filament machine. So with the exception of those couple parts, call it 40 of the parts for each cabin were built using the same nozzle, same layer height, same bead width. And we were fortunate because in this case, we were able to work hand in hand with our customer's engineering team. A nice volley back and forth between their designers and our team to be able to run their designs through our slicer, making sure that all the overhangs were freestanding, that all the wall thicknesses were conforming to the build parameters that we had in place, which was a really important part of success.
Super cool. Looks like Tosin has a question.
I did put it there on the chart. I just want to know whether you've printed in PET or HDPE, and what are the challenges of printing in those difficult materials?
Yes, so we have printed in PETs before. We've printed PETs. I believe it's a PETT. We've only printed glass fiber reinforced versions of those. It's challenging, but we were able to make it work. We've printed a number of PETGs. That's a pretty, it's an easier material to work with, both in filament and in pellet. Although PETG typically has a higher density, so it does put more, it requires more power and torque from your extruder itself. I think the other one you asked was HDPE, right?
That's correct.
Okay, so we have printed 2 different HDPEs. The first time we tried to print HDPE was from a customer who was, as you'd imagine, they were using a lot of HDPE for conventional manufacturing methods. It was an extrusion grade HDPE. This is a marine application, and this is a couple years ago. When we started in pellet, as you would imagine, you say you can print pellets, people will throw everything in the kitchen sink at you. So we came up with this systematic process to identify the printability of a specific material and to identify the fundamental process parameter ranges for that material and the machine configuration we were using. The first material, the extrusion grade HDPE, is one of the only materials that we have to date said this is not a good fit for the process. It warped like crazy. It didn't want to stick to itself. Even with the heated chamber and a heated bed, it was just not a good fit. Now, recently, we've worked with another grade of HDPE that is modified. There's other things in it that I am not at liberty to tell you about, but that actually prints really well. And I know that there's some other HDPEs on the market that are at least being marketed as HDPE materials that are also well lent to the LFAM process. So it's possible. I would encourage anybody who's interested in exploring HDPE specifically to work with a team that is well versed in FGF printing, to work with the material provider and understand how it was engineered, because those things make a big difference.
Okay, thanks for that. Yeah, I think in the case of when we work with recycling plastic, you don't even know who is the manufacturer because it's gone through all the process. True. So that's where the challenge is coming. Anyway, I appreciate the answer. Thank you.
Yeah.
Yeah, it's definitely been a learning curve for us, and yeah, we're just getting into more of the LDPEs as well as the PPs, which Chris can share. So it's good we have this opportunity to share what works and what doesn't amongst us, because I think we have all the same frustrations.
Yeah. Now, we'll be the first ones to, when people ask us about, hey, can you print with this? We're always like, unless it's something we've run, obviously, we go, maybe.
Yeah, it depends.
Yeah, it just depends. And for a long time, I think people just thought that compatibility is based off of where it was on the polymer pyramid, right? Like materials higher up in that pyramid are just more challenging to run. That is true, but also there's a number of materials that are towards the base of that polymer pyramid that are not easy to run, or even versions of materials that are definitely lending themselves better to the process than others. And that's, I don't think, unique to 3D printing, right? Like there's grades of materials that are engineered more for injection molding or extrusion. The same thing is true for pellet fed 3D printing. There are significant improvements to be made, and we've printed injection molding grade versions of materials and then run an LFAM grade of that material afterwards, and it's pretty hard to argue with the results.
Yeah, that's cool. It looks like Chris also, who's we've done a lot of work in this segment of materials as well, had a question. Chris, do you want to share it so we can have it in the recording?
Yeah, of course. Yeah, so as a part of some of the projects that I'm working on, I've also tested printing with a lot of different materials, including polypropylene, HDPE, LDPE, and whatnot. Of course, polycarbonates and PETs as well. And I feel like for the most part, I've been determining printability empirically by actually printing them and laying down a few layers. I was wondering if you run any kind of rheological tests or FTIRs or some kind of tests to determine printability. Are there any like key properties that you look for by any chance?
So when we are testing a new material, again, we run it through our material testing and assessment process as kind of the first stage. And it is cradle to grave. We send materials, a bit of that material out to Brookfield Amatech because we have a moisture analyzer in-house. So we'll make sure we get a reading from Brookfield Amatech, regardless of what the material suppliers say. And we have that reading to start before each and every trial. And then we are essentially running through like smaller designs of experiment from conveyance of that material from the dryer to our hopper, from the hopper to the screw itself. And then we're doing deposition testing at different RPMs, different nozzle sizes.
Mm-hmm.
We'll do essentially print trials after we've honed in on deposition, and that will help us understand not just how the actual material is going to run from like a layer time standpoint, because we are capturing layer time through that process, but it'll also help us understand the design guidelines for that material, right?
Mm-hmm.
So just doing like overhang tests, bridging tests.
Right.
We can typically make parts that can be sent out to be tested afterwards for like mechanical properties. When we're doing material cards, which I did not get into, but it was on that slide, it's essentially our way of being able to provide a much more streamlined method of being able to implement this on a production floor, in which case we are sending materials out beforehand for a number of like rheological tests, DSC, stuff like that.
Got it. Just piggybacking off of what you said, have you ever noticed that some materials print way better on certain nozzle sizes rather than others?
Oh yeah,
Ah,
absolutely.
nice.
Yeah, and especially, it's kind of the funny thing is we have everybody. A lot of people want to start with smaller nozzles, which again we offer 2 millimeter. We've run internally, I think, down to like a 0.6 is just not standard because the smaller those nozzles get, the more the finer the window for processing, especially with how our base extruders are built.
Right.
But when another, I think to complement that, we see a lot of folks who want to use like a carbon fiber reinforced composite or a glass fiber reinforced composite, and definitely how those materials will behave using different nozzle sizes is noticeable and has a direct impact on how the printed piece is going to perform as well.
Right. Thanks.
Of course. Thank you.
Great questions. Does anyone else have a question for Dan? Well, with that in mind, we'll go ahead and turn the recording off. Full disclosure for anyone that's listening, we had a power outage briefly at Re3D, but it looked like the recording stayed on magically, even though some of us dropped off and dropped back on. So hopefully it's all there about halfway through. Does anyone have any questions that they wanted to share without the recording?